phase shift. So when a sine wave does not start at the point where v is equal to 0 at time t is equal to 0, it's said to possess a phase shift. Yeah, the phase shift effectively moves the whole waveform backwards and forwards along the x-axis. So in the first diagram there, the red or the dashed sine wave is a sine wave that crosses the x-axis at a point 0, so that's a sine omega t waveform, y1. The green one actually peaks before the red one, yeah, so it's got a positive angle theta there. It's sine omega t, and that's in brackets, plus theta. It's got a leading phase angle, that's ahead of it, because it peaks sooner. Students often get confused with that. They think because that's that way, that's lagging. No, it isn't. That's leading, because time is going from left to right from it. So that's peaking first. Yeah? Alright, so y2 leads y1 by theta. We can also draw what's called a phasor diagram, where that represents the green waveform, and this phasor at 0 degrees represents the red waveform. Positive angles go anti-clockwise, and that's our phase angle theta in there. On this side, we'll keep the sine omega t waveform in red, so that's that one there, and that phasor there. Y3 is equal to sine omega t. Yeah, but the blue one I'm now going to draw has a a negative theta, because the blue waveform peaks after the red one. Yeah, so it lags. Y4 lags Y3 by theta. Now, just for confusion, we could equally say that Y3 leads Y4. You could turn that talking around depending on which way you want to express it. Yeah? So this blue one is down here at a negative theta angle. It's going that way. Yep. And that's going clockwise. It's moved clockwise. But it's following it, behind it in time. Yeah? So we could here say the red one is leading the blue one, or we can say the blue one is lagging the red. Yeah, we can say the green one is leading the red, or we can say the red is lagging the green. Yeah, whichever suits our needs, really. You usually say what one waveform is relevant to the one that's at 0, if there is one at 0. Yep, alright. So this means that the full equation for an instantaneous value of a sine wave, including phase shift, is, and I'm going to write that out so that's a little bit bigger, little v at time t is equal to the peak voltage times the sine of, open some brackets, omega t plus or minus a phase angle theta, which could be in radians or degrees. If that's omega there, that is always in radians. Yeah. If this bit is an angle in degrees, then the phase shift is also an angle in degrees. But you're not going to come up against that very often in electrical. Alright? Yeah. The other thing that you can come across is a plus or minus a value on the end here. Let's call it C. What that always do is move up and down the x-axis, and in electrical terms, that would be what we call a DC component. That had a DC shift in it, up or down. It's effectively going to move it up or down the y-axis. Yeah? More about that when we do some maths next year, because we were looking at that this morning. Alright? Yeah? But any function can have a component that shifts it, just a constant that shifts it up and down the y-axis. Yeah? So, what we'll do is we'll cap off tonight by having a look at the problem. Yeah. Just pause here. Haven't been given this function here, 335 sine 450 pi t plus pi over 6 volts. We've been given a number of things to find. A, peak value of that waveform. Yeah. No, because that's not a peak-to-peak value, that is the peak value. Yeah. So 355 volts, direct from equation. Or expression, I should say. Yeah. So that requires you to have that knowledge. If you get that question in an exam, you know that that number in front of the sine function is the peak. Yeah, you've got a peak value in the exponential for your capacitor as well, haven't you? That's the applied voltage. Yeah, which is what you head to when you're charging up and what you fall down from when you discharge. All right. B, periodic time. How are we going to find that? Actually, looking at my other answer, it looks as though you need to do C first. It's not been set out in a very good order, really, because you get the periodic time easiest from the frequency. We'll do C first. What have I got in that waveform that's related to frequency? Which bit of this waveform here represents frequency? In the brackets, yeah. T is the time in seconds. Yeah. And remember what the standard form is, that's omega t. So we cross that bit out because we don't want that. Omega is the 450 pi. Yeah. So we say omega is 450 pi. Also, omega is equal to 2 pi f. Yeah. Therefore, f is equal to omega over 2 pi equals 450 pi over 2 pi. And you can see why now I never advocate evaluating pi very often unless I have to, because quite often they cancel each other out. 225 hertz. Yeah. So now we've found the frequency, we can find the period. We can do B period T equals 1 over F 1 over 225 equals whatever that comes out as. 0.004 seconds equals 4 milliseconds. Nearest down it. Yeah. D, we're looking for phase angle theta in degrees. What information have we got in the question about that? Yeah. Theta equals pi over 6 radians. How do we get that to degrees? Well, what you want as an expression, we travel pi radians in 180 degrees. If you do 180 over pi, that's how many radians it is, how many degrees it is for per radian. Yeah. Then if you multiply that by pi over 6, yeah, and what you should really know is that's a standard one, because pi is 180 degrees, so pi over 6 must be 30. Yeah. Alright, I'm going to move on to a new page for the other bits. Yeah, so we're done up to D. So we want E, the value of V at time t when t is equal to 0. So yeah, you just put in value O for t. So we say V at time at 0 is equal to the peak value 335 sine omega times pi times 0, yeah, and then that's plus pi over 6 volts. Yeah. What does this bit evaluate to? Omega times pi times nothing is nothing. So that must equal 335 times the sine of pi over 6. Whatever that comes out to. No. You tell me what you think you got wrong. Yeah. Calculators in degrees, I bet. Yeah. That's better. All right, and if we think about this waveform, right, there's 180 degrees, there's 360. Think about this waveform shifted forward 30 degrees. That's going up to 335 there somewhere. Yeah. Your first answer don't look right, does it? Yeah? So again, that understanding, just think about it. Does that sound like the right answer when this thing is peaking at 335 and after a sixth of a turn, yeah, sorry, a 12th of a turn, is it only going to be, what was your first answer, 4.7 volts? No, that's not. Alright? I mean, at some point it is 3.7 volts. It's about down there somewhere after no time at all. Alright? So, that's that one done. F, value of the voltage when T is equal to 3.5 milliseconds. Yeah? So all we got to do is V is equal to 335 sine omega which is like 450 times 450 pi times 0.0035 plus pi over 6, close brackets. Yeah. So it's just a matter of knowing that you've got to put that in for the time. If you prefer it, you might want to use 3.5 times 10 to the minus 3 in there for the time. Again, your calculator must be in radians. Minus 243 volts. And again, look back. What was our period? What was a complete cycle for this waveform? Four milliseconds. Yeah. So looking back at the diagram, if that's our complete waveform, and finish there somewhere, yeah, and that's 4 milliseconds, and we're talking about 3.5. There's 2, there's 3, there's 3.5. Negative 200 and odd looks about right, doesn't it? Yeah. So again, having that understanding of what this waveform is like and how that function works gives you that ability to be able to sketch something up and just check your answer. Yeah. Right. G. Right, this is looking for T, the time when VT is equal to 100 volts. So what we're looking for is to rearrange this equation. So VT is equal to, I'm just going to use little v in here because otherwise it's going to get a bit cluttery, 335 sine omega t plus theta. Let's put v peak in there for a minute. Because you know me, I'm an advocate of rearranging the equation first and then putting the numbers in afterwards. So, we want t on its own. What are we going to do first? Sure? What's the sine function multiplied by? Yeah. So, we divide by that. We'll move that over with the little v, won't we? Yeah. So we can say little v over vp is equal to sine omega t plus theta. Yeah. Now, how can we get rid of the brackets? What's the inverse function for sine? Sine of minus 1, both sides. Yeah? So we do sine to the minus 1 of little v over vp is equal to omega t plus the phase angle. The brackets are gone. Yeah? What do we shift next? Yeah? Subtract theta. So sine to the minus 1 of little v over vp is equal to minus theta is equal to omega t. And then divide by omega. So I'm going to shift t over to this side because that's what I want to find. Is equal to sine to the minus 1 little v over vp minus theta all divided by omega. Agreed? And then we want to put the values in. So that's sine to the minus 1 little v, we're interested in what the time is when that's 100 over vp 335 minus pi over 6, divide all that by, what was it, 450 pi, don't forget the pi. Plug those numbers in your calculator and see what you get.